Welcome to the third part of Lecture 2, so Lecture 2C. This part will be on molecular geometry, where we are actually looking at the different shapes that molecules form. And the reason we're doing things in the order we are today is in order to do molecular geometry, we need to first do a dot structure, so that's why we looked at that in the previous setup. So one of the terms that we hear when we're looking at molecular geometry is something called VSEPR, V-S-E-P-R, which stands for valence shell electron pair repulsion. And you'll actually see it as the final bullet of this slide because that's just where it fit best. So what do we use VSEPR for? That's how we refer to VSEPR as VSEPR. Well, we use it to predict molecular geometry and bond angles. It's one of the tools we have in order to try to determine molecular shape. And the reason it has its name that it does is we kind of break it apart. VSEPR, valence shell electrons. So we're dealing with electrons from the valence shell. When we put them into dot structures that we just did with our Lewis dot structures, we used electron pairs. And of course, pairs of electrons, since electrons are negatively charged, these pairs of electrons will repel each other. And so these pairs will try to get as far away from each other as they possibly can. And so that's where the term VSEPR comes from. So we're going to work primarily with molecules that have a central atom as far as the shape, but I will show you an example of a molecule, a larger molecule that doesn't have a single central atom, but it has several. So we'll take a look at that as well at the very end. And there's our term, if you needed to see it written out, valence shell electron pair repulsion. So it's getting back to geometry. A couple of things we need to make sure that we examine when we're looking at molecular geometry. The first thing, as I mentioned, is the Lewis dot structure. You cannot do a proper molecular geometry determination using VSEPR without a proper Lewis dot structure. And what we really look at is the number of electron pairs around the central atom. Or electron pairs isn't quite the right term, but really electron regions or electron domains is another way that you'll see that written in different books. And so where these regions of electrons are determine where bonds or lone pairs will form in the molecule. And it's these regions that they repel each other and form certain shapes in order to get as far away from each other as they possibly can. So again, we have steps, and just like we had to do with dot structures, we have to make sure that we follow the steps in order. If we try to do them out of order, then it just won't work. So the first step in finding molecular geometry is to write a proper Lewis dot structure. So once you've got your Lewis dot structure, you look at the central atom and you determine the number of electron groups around that central atom. So electron group, electron region, electron domain, those are all the exact same thing. Okay, now an electron group can be a bonding group. Now a bonding group can be a single bond, a double bond, or a triple bond. All of those types of bonds just count as one single bonding group. Okay, so you don't count it as different number of groups just for a single, double, or triple. They are all just one group. And then any lone pairs around that central atom also count as electron groups. Now we're only looking at the electron groups around the central atom. We don't count any of the lone pairs that are around the outer atoms, only that central atom. And there's the type of bonds that I mentioned earlier. So once we've looked at the number of bonding or number of electron groups, we need to break those out into types of groups. So we want to look at the number of bonding groups and the number of lone pairs around that central atom. So the number of electron groups is going to determine where everything goes, and the number of bonding groups and lone pairs is going to determine where the bonds go and where the lone pairs go. And the last thing we do is we look at a table and find our molecular geometry. So here's a couple of tables here. It's actually one table out of a different book that I teach out of, but I like how their book is organized, or how the table is organized. And so as an example here, if we have, we look at the number of electron groups, we have 2 electron groups here, 2 of those are bonding groups and none of them are lone pairs, then our electron geometry is going to be linear, and our molecular geometry here would also be linear. Okay, look at something a little more complex here. Let's look at 3 electron groups. Let's say that we have a molecule here, SO2. When we do the dot structure for SO2, we have this dot structure here, and we see that we have 3 groups around that central atom. We've got a double bond group, that's still just one group. We've got a lone pair, and we've got a single bond there. So we have 3 electron groups, and so that's a number of electron groups right there. Now, of those groups, only 2 of them are bonding, the double bond group and the single bond group. Those are our 2 bonding groups, and one of those groups is a lone pair group. Okay, so that's how they're broken apart. So our electron geometry, so this is the geometry formed by all the different electron groups, whether they're bonds or lone pairs. All those electron groups will arrange themselves in a trigonal planar arrangement, so basically something like a triangle. However, when we're naming the molecular geometry, we only name it based on where the bonds are. And so when we look at where the bonds are in the molecule, you can see we just have something that looks like that. And so we call that structure bent. It is a bent structure. It does have an approximate bond angle. If we had just a pure trigonal planar like we have above here, we would have 120 degrees between all of those bonds. But what we do get instead is we've got a lone pair sitting up here where that is, and those lone pairs tend to take a little bit extra room, and they repel the bonds down a little bit. They squeeze them a little bit, and so that bond angle is going to squish in a little bit. A good general rule is about 2 degrees per lone pair that's there. So this would probably be right around 118 degrees, give or take, plus or minus in there. Not a hard and fast rule, but that's kind of a good general rule. So that's how we use that table. And we can see we've got different geometries for 4 electron groups. You can see 4 electron groups has 3 different possible geometries. If it has 4 bonding groups and no lone pairs, then its molecular geometry would be tetrahedral, same as the electron geometry. If it has 4 electron groups and 3 of those are bonding, one of those is a lone pair, then we say it's a trigonal pyramid. And if it has 2 bonding groups and 2 lone pairs, then we say that it is bent. Notice that the electron geometry for 4 electron groups is always tetrahedral because those 4 electron groups are always going to arrange themselves in the same way. The only difference is how many of those are lone pairs and how many of those are bonds. And when we name the molecular geometry, we only name where the bonds are. So here's some of our extended octets, our expanded geometries here that have more than 8 electrons around that central atom. And we start to get geometries called trigonal bipyramid if we have 5 groups around there, a seesaw if there's 4, T-shape if there's 3, linear if there are 2. All of those have 5 electron groups around that central atom. And we can get up to 6 electron groups around that central atom. You can see if we have 6 electron groups and all 6 of those are bonds, then that's an octahedral geometry. If we have one of those as a lone pair and 5 of them are bonds, then that's a square pyramid molecular geometry. Or if there's 4 bonds and 2 lone pairs, then we get something called a square planar. But again, notice that the electron geometry listed first there is always octahedral for 6 electron groups. So let's take a look at an example here. And I'm not going to work through the dot structures because that's something you should know how to do from the previous lecture. We will take a look to see how to determine the molecular geometry though. So the first thing that you do is determine the dot structure for water, and you determine the number of electron groups. And then what you find is that you have 4 electron groups around that central oxygen. 2 of those are bonding, 2 of those are lone pairs. So those 4 groups will arrange themselves in a tetrahedron because that's the farthest they can get away from each other. So it looks like a 3-dimensional triangle. Okay, that tetrahedron is the electron group geometry, not the molecular geometry, because that just looks at where all of the electron groups are. The molecular geometry only looks at where the bonds are. And we see that we have two bonding groups and two lone pairs. Those two bonding groups form something that is called a bent geometry, and that's exactly what the table would find. The bond angle here is going to be right around 105. If there were no lone pairs there, then we would have about 109, but each of those lone pairs squeezes in about 2 degrees, so that puts us right around 105. And that's pretty close to where water actually is. So here's our example of what the geometry looks like. So if we had just an oxygen with those 4 lone pairs around it, we would have a lone pair there, here, and here, and here, and they would be 109.5 degrees apart. With the bonding groups in there like this, they take up a little bit less room, and they don't repel each other quite as much. And then you've got these big old lone pair groups out here that take up quite a bit of space, and they are going to repel those bonding groups in just a little bit. We can see we estimated about 105, and we see that water is actually about 104.5, so it squeezes in quite a bit. Another example here, ClO3, so that's a chlorine and 3 oxygens. It does have a negative charge on there, which makes the dot structure just a little bit more difficult. The only thing that's more difficult there is that negative charge. That negative charge indicates that that molecule had to have an extra electron to make the bonding happen appropriately. And so when you're adding up when you're doing your dot structure, and you're adding up your total number of electrons, you have to add in that one extra electron to account for that negative charge. So you do the dot structure. What you find is, again, 4 electron groups. The electron group is going to be tetrahedral around the chlorine, the first atom listed there. Okay, but different from the water had 2 bonding pairs and 2 lone pairs. This molecule has, or this ion, has 3 bonding pairs and 1 lone pair. And when you look that up on the table, what you find is that the molecular geometry is trigonal pyramid. And so the bond angles here are about 107 degrees. We have that 1 lone pair around the center. Now I know this picture is for ammonia, but it has the same geometry. So if you can imagine that this is actually a chlorine here, we'll scribble that out and put a Cl right there, and do the same thing over here. There we go. Although those are oxygens there, so we'll make those oxygens and oxygens and oxygens. There we go. Now it's this right molecule, but it looks terrible. So we have the same idealized tetrahedral geometry for the 4 electron pairs that we have around that central atom, but now we just have that 1 lone pair. It does squeeze down all of those bonds, but not quite as much as what 2 lone pairs did. And so the actual geometry is right around 107 degrees, which is pretty much what we would have predicted by subtracting 2 degrees for each lone pair. So that works out fairly well. And here we have BRF3. So again, we want to do the dot structure, same as before. What we find, big molecule, we have 5 electron groups. So when you do this dot structure, what you're going to find is that you complete the octets for all of those fluoride atoms, or fluorine atoms rather, around the bromine, and you still have 2 electron pairs left, or you have 4 electrons that you haven't placed anywhere, and you have to put them in pairs. And remember, our rules say that if you have electrons left over, you place them in pairs around the central atom. So we put 2 more electron pairs around that bromine. And so we have 5 total electron groups around that bromine. And so the electron group geometry there is going to be what we call a trigonal bipyramid. It's like 2 pyramids with triangular bases stuck together. And when we look at the types of groups we have around that central atom, we have 3 bonding groups and we have 2 lone pairs. When we look that up in the table, it tells us that that molecular geometry is going to be a T-shape. And here's a picture of that geometry there. And so we have, looks like I cut a little bit of that off over here. But here are our 5 electron groups. We've got 3 bonding groups. We've got 2 lone pairs. So our electron group geometry is going to be trigonal bipyramidal. It's not a very good picture, but you get the idea. Now, when we're looking at the molecular geometry, we want to look at what's the geometry formed only by where the bonds are. And we see that it's something that's called T-shaped. If they had rotated at 90 degrees, maybe it would be better so that you had an F, BR, an F, and an F there. So now it looks more like a T. So that would be an expanded geometry, or an expanded octet type geometry. We have that trigonal bipyramid. Now, I mentioned that a lot of times we have only central atoms, but as you start going into other types of chemistry, specifically organic chemistry, where you have lots of atoms strung together and you have molecules that are very long chains, a lot of times you want to look at what's the geometry of a particular atom in the middle of a chain. And so all of those atoms within a chain can be central atoms, or we call them interior atoms since they're not truly central. They're central to the things around it, but they're not central to the molecule by any means. And so when that happens, we look at the geometry of each individual atom that's in that interior chain. And so the molecule itself doesn't have a geometry. So if you have like a molecule of hexane, we wouldn't say, well, it's tetrahedral geometry because all the carbons are tetrahedral, but the molecule itself would not be. Okay, so those molecules don't have a single geometry, but we do concern ourselves with the geometry of each of those interior atoms. Pretty picture there. There we go. And so here's molecule glycine. We see we've got 4 interior atoms. We've got the nitrogen here, the carbon here, another carbon here, and oxygen here. Okay, so those are our 4 interior atoms. And as we look at the number of electron groups around each one, for the nitrogen here, we've got 1, 2, 3 bonding groups and a lone pair. And so that's 4 electron groups around the nitrogen. 1 of those is lone pairs, 3 of those are bonding. And when we look that up, we see that the geometry is a trigonal pyramid. And for the carbon that's here, we see it has 1, 2, 3, 4 bonding groups with no lone pairs. So that atom would have a tetrahedral geometry around it. The next carbon here has 1, 2, 3 bonding groups around it. Remember, that double bond that's there only counts as 1 bonding group. And so we just have the 3 bonding groups and no lone pairs. So that carbon atom would be trigonal planar. And then the oxygen here has 1, 2, 3, 4 electron groups around it. So 2 of those are bonding groups, 2 of those are lone pairs, just like in water. And so we have a bent molecular geometry around the oxygen there. And here's an example of what that molecule looks like. Here, the nitrogen, you see the trigonal pyramid geometry there. For this carbon, we see the tetrahedral geometry. For this carbon here, we see that trigonal planar that forms a little triangle there, but they're all in a single plane. And then for the oxygen, we see that the connections are in fact bent. Okay, so some complex stuff with molecular geometry. It's something it's kind of fun to get a handle on. If you are going to move into a little more chemistry in your career here at MSP, specifically organic chemistry, any kind of biological chemistry, you definitely want to be able to look at a molecule or look at an atom and do a very quick assessment on what type of geometry it has. It will really help you out in those classes. So if you have any questions on how to do any of this content, please let me know, and I will see you on the next video.